In this lesson, we'll examine stoichiometry and solution chemistry, gravimetric analysis, and titrations. Gravimetric analysis is simply an analytical technique that's based on the measurement of mass. So it's an experimental technique. And what's going to be important that you know in order to do gravimetric analysis are your solubility rules. Because what you're going to see is the reactions that you study often involve the formation of a precipitate, and you'll need to use the solubility rules to identify the formation of the precipitate so that you know what substance will be a solid in your experiment. Now, the process of stoichiometry is the same as it's always been. As you have seen already, we can combine using mass quantities or gas data in order to follow the flow of stoichiometry. Now that we have a new relationship of concentration and volume that can be used to identify the quantity of moles in a particular solution, we can use that data in order to do stoichiometry. So this flow chart will look familiar, although when we first learned stoichiometry, we simply said that we have the mass of quantity A, and we're using that to find the mass of quantity B. This time, we're just going to use the word quantity because we can be given information like their mass or their concentration and volume, and we can be asked to find their mass or their concentration, for example. The steps are going to be the same. The first step is always to use the data that we're given to find the moles. The formula that we use in order to find the moles of our initial substance depends on what we're given. Once we've got the moles of one substance, to find the moles of any other substance in the balanced equation, as you know, we use the mole ratio identified by the coefficients in the balanced chemical equation. The third step, calculating the quantity that we're asked for, we'll use the moles and we'll use the other data in the question in order to calculate what we need to. Let's do some practice. In this first example, we want to know how many grams of zinc chloride will be produced when 1.05 liters of a 2 molar hydrochloric acid solution reacts with zinc in the reaction below. So we're given a volume of 1.05 liters of hydrochloric acid, and we've got a concentration of 2 mole per liter, or 2 molar. So this is our quantity A. We know how much hydrochloric acid we have, and we're being asked to find out the mass of the zinc chloride that is produced in this experiment. So the first step is to find the moles of our hydrochloric acid. So to find the moles of our hydrochloric acid, because we're given the concentration and the volume, we're going to do C times V. Our volume is given in liters, so we don't need to make a conversion here. So we've got 2 times 1.05, which gives us a quantity of moles of 2.01. So we've got 2.01 moles of hydrochloric acid that have reacted. In our second step, we need to use the mole ratio to figure out how much zinc chloride is produced in this reaction. It's a 2-to-1 ratio, so that means that the moles of zinc chloride is going to be half the moles of hydrochloric acid that we used in the experiment. So therefore, we will be able to produce 1.05 moles of zinc chloride. In our third step, we need to find the quantity we're asked for. So in this case, we're being asked for the mass of the zinc chloride, which, as you know, the formula is moles times molar mass. So we're going to take the moles and we're going to multiply by the molar mass of zinc chloride, which is 136.29. When we multiply this, we get 140 grams reported to the correct number of significant digits. In the second example, we're being asked for the mass of the precipitate that will be formed when 75 milliliters of 0.8 molar sodium hydroxide reacts with 85 milliliters of 0.75 molar copper sulfate solution. Now we're not given a reaction here, so what we need to do is write out the reaction first. So I've got sodium hydroxide, and I'm reacting it with copper sulfate. As you can see by observation, this is going to be a double displacement reaction. So we've got our copper, which in this formula is 2 plus because of the sulfate, which is 2 minus. And I'm going to combine that with the hydroxide, which is 2 minus. So the copper hydroxide that's produced here is CuOH2. And the other product is sodium sulfate. Sodium has a +1 charge, and sulfate is -2 in its charge, so we produce Na2SO4. Now the question asks us for what mass of precipitate, so we need to identify which one of these is going to be the precipitate. If you use the solubility rules, you'll see, and this is just good for practice, you'll see that sodium hydroxide is aqueous, based on the rule that all compounds of the alkali metals are soluble. For the sulfate, all sulfates are soluble except if they're combined with lead, calcium, strontium, mercury, or barium. So that means that copper sulfate is going to be soluble or aqueous. Copper hydroxide, so rule number 5 is that all metal hydroxides are insoluble except if they're with group 1A, calcium, strontium, or barium. So that means that this is our precipitate. And again, sodium compounds are always aqueous based on rule number 1. So what we have here is 75 milliliters of our sodium hydroxide, and it's 0.80 molar. And then we've got 85 milliliters of our copper sulfate, and it's 0.75 molar. And as you might see or recall, this is going to be a limiting reactant problem. We're being given information about both reactants, so we don't know which one is controlling the reaction. So we need to identify which one is the limiting reactant. So to do that, we can set up our table to organize our data. So we've got our reactant, our moles of our reactant, our moles of our product, and in this case, we're going to use the copper hydroxide because that's what we are trying to find the mass of. And then we're going to decide the status of the reactants. So our first reactant here is sodium hydroxide, and our second reactant is the copper sulfate. Before we go any further, we should just balance this. We need a 2 there. So to find the moles of sodium hydroxide, I need to multiply the concentration by the volume, and I need to make sure that I put my volume into liters. So I find that I have 0.060 moles of sodium hydroxide. Same thing for the copper sulfate, the concentration times the volume put into liters, and I am left with 0.06375. To find the moles of the product, I need to apply the ratio. So for the sodium hydroxide, it's a 2-to-1 ratio. So my moles of sodium hydroxide are 0.030. And the copper sulfate and copper hydroxide are in a 1-to-1 ratio, so the moles of copper hydroxide based on the copper sulfate is 0.06375. At this stage, I can see that my limiting reactant is my sodium hydroxide, so the actual amount of product that I can produce in this case is 0.030 moles. In my last step, I can find the mass of the copper hydroxide, so I can multiply the moles of the copper hydroxide that I'm able to produce, and multiply by the molar mass, which is 97.57, and I find that I'm able to produce 2.9 grams of the copper hydroxide. So this setup is exactly the same as it was in the previous unit when we studied limiting reactants. The difference is that we're dealing with concentrations and volumes instead of only being given the masses. In example 3, this is specifically an example of what we would refer to as gravimetric analysis. So we're using masses in order to study a sample. We've got an ionic compound that contains chloride ions and an unknown metal. So I'm just, for the purpose of studying this, I'm just going to call my metal M, and I know it's a chloride of some metal. And I'm starting with 0.5662 grams of this. And we study this by dissolving it in water, so it's aqueous, and then reacting it with silver nitrate. And silver nitrate is also aqueous because of the nitrate. All nitrates are soluble. So when we do this double displacement reaction, we're going to produce AgCl, and we're going to produce the nitrate of M, which is also going to be soluble. So the metal that I have here is really irrelevant in this question. I'm not too concerned about it. Now this is a precipitate. Chlorides are soluble except with silver, lead, or mercury. So in this case, being combined with silver, you're going to get a precipitate of silver chloride. When we do this reaction, we produce 0.0882 grams of the silver chloride. The question is asking us to determine the percent by mass of chloride in the original compound. So I want to use this information to figure out the mass of the chlorine that is in this original compound. So my first step is to figure out how many moles of silver chloride I'm dealing with here. So I'm going to divide by the molar mass. And the molar mass of silver chloride is 143.32. And I find that the moles of silver chloride that I found or produced was 6.15 times 10 to the negative 4. Now the moles of silver chloride that I produced is also equal to the moles of silver that were produced, because there's a 1-to-1 ratio. For every mole of silver chloride that was produced, there is 1 mole of chlorine. And all of the chlorine that is trapped in the silver chloride precipitate was sourced from this compound. So I now know that the moles of silver chloride in this original sample is 6.15 times 10 to the negative 4. So I can figure out the mass of just the chlorine in that particular sample by multiplying by its molar mass of 35.45. And we find that there are 0.0218 grams of chlorine in the original sample. So to figure out the percent of chlorine in the original sample, it's a matter of dividing by the total mass, and we find that it's 3.85% by mass. And this is an example of gravimetric analysis, as I said, because you're doing an experiment where you collect some kind of mass. So those are some basic problems in stoichiometry. And what we're going to do is talk about another technique in chemistry that is called titration. And titrations are a technique that are used to determine the concentration of an unknown solution. The way that you do a titration is you have a solution of known concentration, and you react it with a solution of unknown concentration until you know that you have exactly the proper amounts of both reactants in your flask. So you want to add just the right amount of your known, for example, to your unknown solution so that they are perfectly reacted based on their stoichiometric ratio. When you've got this complete reaction, then you're going to be able to use the data that you've collected in the experiment in order to calculate the unknown concentration. When you do an acid-base titration, that's a specific type where we're dealing with a reaction between an acid and a base. And so we're going to have a known solution. For example, we might have a known solution of acid, and we're going to react it with an unknown solution of base to identify its concentration. Specifically, an acid-base reaction is a double displacement reaction. So you'll see it as that. You know how to recognize an acid and a base. And they're both really ionic compounds. So it's a double displacement reaction. It produces salt and water. Now, when we're doing a titration, and you're going to be doing these in the lab, so you'll become very familiar with them, you're going to be using a piece of glassware that's called a burette. And it's like a really tall graduated cylinder. So you can see the bottom part of one here. And it's got what's called a stopcock on it. And the stopcock is used to control the addition of the solution in the burette to the solution in our other flask. This way, we can have our unknown down here, and we can add a very controlled amount of solution into the flask until they're perfectly reacted. We're going to use an acid-base indicator in order to help us to know when the substances have perfectly reacted. The point at which they've perfectly reacted, so the moles of the reactants are in stoichiometrically equal amounts, is called the equivalence point of our titration. And the indicator, as you've seen before using phenolphthalein, is a substance that changes colors in acids and bases. So we're going to use it to help us to identify when a solution has changed from being acid to base. When we see in a titration a color change because of our indicator changing color, we refer to that as the end point of the titration, because we're going to know that that's when we're going to stop titrating or stop adding the solution from the burette into the flask. And what we want is for these 2 points, the equivalence point and the end point, to be as close together as possible. Because we want the point where we stop the titration because of the color change to be very close to the point where the moles of each of the substances are in stoichiometrically equal amounts. Now, initially this might seem a little bit overwhelming, but at this stage you really don't need to worry too much about all of the details presented here. You're going to have a lot of practice in the lab with titrations and have a lot of time to process this information. Now what we're going to do is look at how the information would be presented to you if you're doing a titration calculation based on some lab data. When you do a titration, you're going to be adding controlled amounts of solution from the burette. And the way that we read the burette is we start at 0, and so we make an initial reading, and then we allow the solution to leave, and we read where the solution is when we've stopped the titration. So say, for example, I start at 0, and I allow the solution to leave the burette and stop when the solution is at 10. That means that I've added 10 milliliters of solution. If I do a second titration and I stop at 15, then in this case I know that I've added 5 milliliters of solution. And I can see that by taking my 15, where I finish my final reading, and subtracting my initial reading of 10. Now, when we do titrations, we're going to end up doing more than one trial if possible. It's always best to, in order to obtain precise results, whereby we get several sets of data that are repeated, we need to do more than one trial. So when you do a titration, you're going to have a data table that looks something like this, where you have your readings from your burettes from your different trials. For each trial, you have a final reading and an initial reading of the burette. And in order to figure out how much solution was added from the burette, you need to find the difference between these two values. So for example, in this case, the amount of solution that was added from the burette, 20.62 minus 6.55, is 14.07. In this case, we've added 13.93. And in this case, we've added 13.88 milliliters. Now, what you want is for your data to be quite precise. And these are reasonably precise in terms of their closeness. Now, what we had in this scenario, we're doing a titration of HCl by calcium hydroxide. So what that means is that in the burette, we had the calcium hydroxide, and in our flask down below, we are reacting it with hydrochloric acid. And in each trial, we put a fresh 15 milliliters of hydrochloric acid into the flask. And our solution of known concentration in this case is the calcium hydroxide. I know the concentration of my calcium hydroxide. So what we're going to do now is use this data in order to find out what the concentration of the hydrochloric acid that we are studying must be. To start, we need to write a balanced chemical equation for the reaction that we're studying. We've got hydrochloric acid, which, by the presence of the H in the formula, you know is your acid, and calcium hydroxide, which you know by the presence of the hydroxide is your base. And as I said, you'll recognize this as a pretty routine double displacement reaction. So the calcium has a 2+ charge, and the chlorine has a -1 charge. So we're going to produce calcium chloride. And the H and the OH are going to make our other product, which is going to be water. So as you can see, when you react an acid with a base, you produce a salt and water. Next, I need to balance this equation. So I get 2 hydrochloric acid plus the calcium hydroxide. The next question asks us to find the average volume of base added in the experiment. So in trial 1, we added 14.07 milliliters. In trial 2, we added 13.93. And in trial 3, we added 13.88 milliliters. So to find the average, we need to take the sum of all of them, and we need to divide by 3. And we are left with 13.96 milliliters. Now at this stage, what I'd like you to make note of is that all of the volumes that you've been given have been reported to 2 decimal places. And that's going to be really important because every time you read a burette, you're going to report 2 decimal places. As you'll recall from our study of accuracy and precision, when we take measurements, we always read one beyond what the gradient provides us with. When you read a burette, it's to the tenths, and then you're going to be able to estimate 1 digit further. So every time you make a reading, you should have 2 decimal places. In the last step, we want to determine the concentration of our unknown sample of acid. So what we were given, we were titrating this volume, which was 15 milliliters. And we want to know the concentration of the hydrochloric acid. We know that the concentration of the calcium hydroxide is 0.824 mole per liter because it's given to us. And now we know the average volume that we required in order to react these two substances perfectly with one another was 13.96. Now at this stage, you may be very tempted just by the setup of the problem to use C1V1 equals C2V2. That formula is for dilutions. And that formula should be left to only for dilutions because in that case, the moles of your original solution and your final solution are the same. Because of stoichiometry and the ratios in the balanced chemical equation, the ratio of the acid and the base is not always going to be 1-to-1. So I caution you to not use C1V1 equals C2V2 and to go through the process and find the moles and apply the ratio. So in this case, for the calcium hydroxide, the moles is equal to C times V, which is 0.824 times 0.01396 because I need to put my volume in liters to properly calculate the moles, and I'm left with 0.023006 moles. Now you may notice that the data that we're dealing with is quite precise, and that's the nature of doing a titration. Every value that we have, every piece of data that we use when we're doing a titration is as precise as possible. And we use very precise equipment, as you'll see when you do a titration, in order to maximize the precision. So the moles here, I apologize, I wrote down the wrong number. The moles here is 0.115 moles, and this is the moles of the calcium hydroxide. The ratio is 1-to-2, so the moles of the hydrochloric acid is going to be 2 times that, which is the 0.023006. And in the last step, we want to figure out the concentration of the hydrochloric acid. And this number of moles is the moles of hydrochloric acid in 15 milliliters of the hydrochloric acid. So we can use our formula of C is equal to N over V in order to find the concentration of this solution. And the concentration of the hydrochloric acid is 1.53. And limited to 3 significant digits by the concentration of the calcium hydroxide.